Okay, so let's now just end up this discussion with one more example in lecture, and then I'm going to post a little video that takes you through a few more examples. You can follow those on your own. Let's end with another polyatomic ion, PO4 3-. This is the phosphate ion. Many of you who are also in biology classes probably see the phosphate ion a lot. Let's build the best Lewis structure that explains the most stable arrangement of the valence electrons in this polyatomic ion. How many valence electrons does phosphorus bring in? 5. How many does the oxygens bring in? 6 for each one, and there's 4 of them. So we've got 4 times 6 is 24. And what else do we need to account for? We need to add 3 more, because overall, this polyatomic ion has a net 3- charge. So there's 3 more electrons than we would have expected to be there just based on the protons in phosphorus and the 4 oxygens. So we need to add those 3 more electrons. So that gives us 24 and 8 is 32 valence electrons that we need to place. So are we going to go linear or spokes on a wheel? Spokes on a wheel, and who's in the center? So we're going to put phosphorus in the center, surrounded by the oxygens. That gives us 4 bonding pairs. That uses 8 of our 32 electrons. And now we're going to place the rest following the rules that I told you. Keep them in pairs and fill up an octet on one before you move to the next one. And you don't put anything on the center. No lone pairs on the center unless you have to. And you don't make any double bonds or triple bonds until after all of your lone pairs have been placed. So that's 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. So we didn't have to put any on phosphorus. So we don't need to worry about is phosphorus going to be hypervalent or not. Can phosphorus be hypervalent? Yes or no? Who thinks phosphorus can be hypervalent? Raise your hand. Who thinks phosphorus cannot be hypervalent? Raise your hand. Who forgot what hypervalency is? Hypervalency is when we represent a molecule where one of the atoms has more than an octet of electrons associated with it. So more than 8 electrons. We've expanded the octet. And elements that are in n equals 3 or higher will experience hypervalency in some compounds in nature. Yes, question. Phosphorus could be hypervalent, but as I'm showing right now, it's not. Right now, the way I'm showing it is with a full octet. But wait, there's more. So, okay. I do need to also put brackets around this to show that overall, this has a net 3- charge. And you might be tempted to stop right here because we've placed all the valence electrons. We haven't broken any octet rules. Okay. We've accounted for everything. It looks good, right? But now let's take a look at the formal charge. So the formal charge is now pattern recognition. What's the formal charge on an oxygen that's got 1 covalent bond and 3 lone pairs? If you don't remember, go ahead and count them up. It should be what? -1. Okay. If you count them up, oxygen brings in 6 valence electrons, and each one is surrounded by 1, 2, 3, 4, 5, 6, and then half of these 7. So as drawn, this Lewis structure, all of these oxygens have a 1- formal charge. Now we can figure out what the formal charge on the phosphorus would be in this drawing, because we know that overall it's got to be a net 3- charge. So you can just do that, right? It's 4- right now, so the phosphorus has to be a 1+ for it to net out to be 3-. Or you can calculate the formal charge. Phosphorus brings in 5 electrons, valence electrons, and it's surrounded now in this structure with 4. So that gives it a +1. Now that's a lot of formal charge. So let's see if we can reduce the formal charge by now taking a lone pair from one of the peripheral oxygens and bringing it into a shared pair. And you might hesitate, wait, why should I do that? I've got a full octet, right? You're doing it because you're going to see if you can reduce overall the formal charge. And we can do this with phosphorus because phosphorus can be hypervalent, right? It's an N equals 3 or greater. So we can do this. So let's see what happens. Can we reduce the formal charge? So let's just take one lone pair and let's just do this one at a time. I'll take the one from the right, but I could have taken this one lone pair from any of those 4 oxygens. Let's just do it for one. That would give me a structure that looks like this. And don't be lazy. Spend the time and put all of your lone pairs in very clearly. Now, if you count these, there will still be 32 overall. So I haven't dropped any. Now, let's assign the formal charges. If you didn't change what one of the oxygens looked like, you don't need to count it again. And if you do the pattern recognition, you'll know that an oxygen with 1 bonding pair and 3 lone pairs will have a formal charge of 1 minus or -1. And this one, a double bonded oxygen with 2 lone pairs, that has a formal charge of 0. And the phosphorus that came in with 5 electrons, and now it's surrounded by 5 electrons. 1/2 of each of those 5 shared bonds, okay? So this is 0. So that's good. We've made some 0 formal charges. So we're lowering the number of non-zero formal charges. That's good. Let's see if we can get it even better, shall we? Let's do another one. And I like being symmetrical, so let's start with some symmetry. Let's go on this side. Let's do this one more time. Right? All I'm doing is moving a lone pair into a shared pair. So I know that if I do this carefully, I've kept track of all 32 electrons. But as you're practicing this, go ahead and count the electrons each time you make a manipulation to make sure, hold on, to make sure that you're following or not losing anything. 3 minus. Now let's take a look at the formal charges. Again, for the oxygens that we haven't done anything to, we know that those are 1 minus. Here, let's be consistent. -1, -1. The oxygens with double bonds and 2 lone pairs are 0 and 0. Now what's the formal charge on the phosphorus? It's -1. Because it has to add up to 3 minus, and phosphorus brings in 5 valence electrons, and now as drawn, it's surrounded by 6. So look what we've done. It still looks just as stable as the first one, right? All 3 of these look stable as far as satisfying the octet rule, or these last 2, of course, are expanding the octet, but we can do that with phosphorus. But look what we've done now with the formal charge. We still have 2 zeros and 3 -1s. So that is no different from the one I have there in the middle. But what is different is now I've got the negative formal charge on the lower electronegative atom. Okay, this one puts the negative formal charge on the lower electronegative atom. So it's not as favorable as the one in the middle. The one in the middle, this is best because it has the fewest number of non-zero formal charges, and it's putting the negative formal charge on the more electronegative atoms, not the least electronegative atoms. So if we were to say, take this one step further, and now what would you expect to find experimentally? If we measured the bond order of this, what would we expect to find? How many bonding pairs are there? There's 1, 2, 3, 4. There's 5 bonding pairs. 1, 2, 3, 4. There's 5 bonding pairs. And those bonding pairs are distributed across how many atom pairs? 4 atom pairs. So the bond order is 1.25. And that matches what we find experimentally. Now, if you were to actually draw the formal Lewis structure of the phosphate polyatomic ion, you would draw 4 different resonance forms with double-headed arrows showing that it looks like this, but you represent that there's 4 different ways that that double bond could have arose from the lone pair coming from one of those 4 oxygens. But in reality, it's not that you've got 4 different structures that are all bouncing back and forth. In reality, you've got 4 bonds that are exactly the same. These are going to have 4 equal hybrid bonds. It's not 1 double bond and 3 single bonds that are just kind of dancing around this and switching positions. They're all 4 bonds have the same bond length, and they have the same bond energies, the same bond strength. And it's somewhere between that of a single bond and that of a double bond. So it's a hybrid between those, okay?
The sulfate ion, SO4, with an overall 2 negative charge. This is a polyatomic ion. And let's just do things step by step. Step 1, identify the valence electrons. So we've got 6 from the sulfur. We have 4 oxygens, and each one of those is 6, so that's 30. Plus, we need 2 more because overall, this polyatomic ion has a net 2- charge. So that gives us a total of 32 valence electrons that need to be placed on our structure. The most favorable structure will be with sulfur in the center, surrounded by the oxygens. So let's start with that. And by connecting everything with a single bond, that places 8 of our 32 electrons. So then let's start placing the rest around the outside. So we have 8 placed, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. There's none left over to be placed on the central atom. All of the octets are satisfied. What we do need to show overall is that this structure has a net 2- charge. So we show that with the brackets and the charge shown in the upper right. Now that looks satisfactory, but now let's take a look at the formal charges. The formal charge on any of these oxygens, the oxygens have 6 valence electrons, but right now they're surrounded by 1, 2, 3, 4, 5, 6, 7 electrons. That gives us a total formal charge of -1. So each one of these oxygens has a formal charge of -1. On the sulfur comes in with 6 valence electrons, and it's surrounded by 1, 2, 3, 4, half of the electrons from the shared pairs. So that gives a formal charge on the sulfur as a +2. So overall, that's just too much formal charge on any of the atoms, especially when we know that we can reduce the formal charge by bringing lone pairs from the outside atoms into shared pairs on the central atom. So let's go ahead and do that. Let's just take one lone pair. Let's take this one up here and move it in. That would look like this. And if we assign formal charges, well, it will still be -1 for all of these oxygens with a single bond. Now the oxygen with a double bond and 2 lone pairs will now have a formal charge of 0 because that one came in with 6 valence electrons and now it's surrounded by 1, 2, 3, 4, and then half of these, 5, 6. 6 minus 6, formal charge of 0. The sulfur is now going to have a formal charge of +1. You can work that one out for yourself. Overall, these still add up to an overall net charge of 2-. So let's do it with another lone pair. Let's see if we can get the formal charges even lower. Let's take from the opposite side, and that would look like this. Notice that in each case, we still have a total of 32 electrons placed. Now if we assign formal charges, we still have a -1 on these 2 oxygens that we didn't do anything with. Now the oxygens with double bonds, those have a formal charge of 0, and now you can count that the formal charge on the sulfur is 0 as well. So this one looks even better still. So what would it look like if we took another lone pair from an oxygen and bring it in to the sulfur? We can do this on sulfur because sulfur can have an expanded octet. On sulfur, it can take more than 8 valence electrons. It's hypervalent. And of course, sulfur can do this. Sulfur is in period 3 or greater. So let's see if we can reduce the formal charge even more by bringing in more double bonds and reducing the formal charge on the oxygens. That would look like this. We still have 32 electrons placed, and now let's look at the formal charge. Still -1 on this oxygen with only one bond, and all the other oxygens now have a formal charge of 0. What's the formal charge on the sulfur? Well, sulfur came in with 6, but now it's surrounded by 1, 2, 3, 4, 5, 6, 7 electrons, half of the electrons in the shared pairs. So that's 6 minus 7 is now a formal charge of -1 on the sulfur. Now overall, we still have a net 2 minus charge. If we were to take it one step further and bring in a lone pair from all the oxygens, that would look like this. And now if we look at the formal charges, there's 0 on all of the oxygens, and on the sulfur, now we would have 2 minus. So looking at all of these options, this one here is still the best option because you want to consider that any negative formal charge is going to be found on the most electronegative atom. And in this case, that's oxygen. Now this last structure isn't as favored because we have 2 formal charges on any one atom. So you want the formal charges to be 0 and you want them to be as low as possible on any given atom. That's going to overall give you your most stable configuration. In fact, if you look at them closely enough, you'll realize that there are 6 total resonance forms that you could have. Now, that's a lot to draw out, and I don't think I would ask you to ever do that on an exam, but in this video, I could speed things up. So let me show you what all 6 of those would actually look like. And there you have all 6 resonance forms, and we can even describe what the bond order would look like. The bond order would be, in any one of these, we have 1, 2, 3, 4, 5, 6 bonding pairs of electrons, and we have overall 4 bonds showed. So that's 6/4, which is equal to 3/2, which is a bonding order of 1.5, meaning that all 4 bonds will actually be the same bond length, and they'll have the same bond energies, and it would show about 50% would be a single sulfur oxygen bond length and bond energy, and 50% would be of a double bond. In other words, it would be a hybrid, and the strengths and the lengths would be about halfway between the length and the energy of these 2 bonds. Let's do the nitrate polyatomic ion. 5 valence electrons coming in from the nitrogen, plus 3 times 6 valence electrons from the oxygen, plus 1 from the extra electron that gives us the overall net negative charge. That's 18 plus 6 equals 24 electrons. We'll have nitrogen in the center, surrounded by the 3 oxygens. That places 6 valence electrons. Let's put the rest in. 8, 10, 12, 14, 16, 18, 20, 22, 24, and we're done. We've placed all the electrons. Let's show that this overall has a net negative charge. Notice that the nitrogen in the middle does not even have a complete octet. Let's just go ahead and satisfy that octet by bringing in a lone pair from one of the outside atoms that have a full octet and bring that into a shared pair. That would look like this. We now know that this oxygen with the double bond has a formal charge of 0, and the oxygens with a single bond will have a formal charge of -1. The nitrogen comes in with 5 valence electrons. It's only surrounded by 4, so the nitrogen would have a formal charge of +1. Notice that these still all add up to 1 minus charge. Could we reduce the formal charges more like we did with the previous 2 examples? Well, we really can't, because if I were to bring in another lone pair from the outside, that would give us too many electrons on the nitrogen. Nitrogen cannot have an expanded octet. It's only in the second period. Depending on how you think about hypervalency and which models that we use to explain it, the model I introduced you to was just the idea that you have d orbitals available for those extra electrons. Next semester in chemistry, you'll learn about other models that will also explain hypervalency. But in this case, nitrogen doesn't have extra orbitals. There's no more room for those electrons to fit in with that atom. So nitrogen cannot have an expanded octet. So that is not an option to us. We are left with the structure that we had here. Even though we have these formal charges, this is the best we can do. But now we do need to recognize that that lone pair that I took up here could have been taken from any of those three oxygens. We demonstrate that by showing the resonance forms and showing all the other possibilities for the arrangement of these electrons around the same structure of atoms. This represents that there are three different arrangements of the electrons. They may all look the same to you if you just rotate it, that's true, but this demonstrates that the lone pair could be shared from any one of three oxygens. And if you were to experimentally measure the bond lengths and the bond energies of these nitrogen-oxygen bonds, you would find that all three would be the same. They're what we call a hybrid between the double and the single bonds. And we can calculate that bond order. It's going to be the number of bonded pairs. That's going to be 1, 2, 3, 4 bonded pairs, divided by the number of bonds. In this case, we have 2 single bonds and 1 double bond, so that's 3 bonds. That gives us a bond order of 1.33.